Hello, and welcome to the Chapter 6 review. So keep in mind, guys, this is the last in-class test I'm going to give you. There might be maybe a quiz or two left for the semester, but this is the last test. And then you guys will obviously have a semester final exam. But anyway, Chapter 6, let's see how good we can do on this one. So, like many times before, I prepared a video walkthrough, and just kind of, these are good questions to study if you want to get prepared for the Chapter 6 test. So first things first, let's actually jump to vectors. That's 6.3. And let's think about these different ways of viewing vectors and different things you can calculate. So you can define a vector with the starting and the ending point, right? So 2 points define a vector, one where you start, one where you end. Those are just the coordinates of those points, but then we also have the component form. So the component form says this is basically sort of how big your vector is and what direction it's going, right? So if you have the points, how do you get to the component form? Well, for the first component, right, you would do 2 minus 1, right? And for the second component, you would do 7 minus 2, right? So you always take the numbers at the end point and subtract away the numbers at the starting point, right? So we did 2 minus 1 and 7 minus 2. And that's always how you can get the component form if you're given 2 points like that. So this would be 1, 5. And that right there is the component form. The component form basically just shows you sort of what your arrow actually looks like in space. And obviously you can graph this, right? So on the x-axis, it tells me my arrow goes 1 unit to the right, and then it goes 5 units up, right? So it's going to go sort of up there. So if we're starting at the origin, I know we have a different starting and ending point. I'll get to that in a second. But if we started this vector at the origin, right, that would be what the arrow looks like. Now, if you want to get more specific, right, this vector PQ, it says specifically it starts here, right? This is point P. And then point Q, you have to go 2 more notches up, looks like. But if you go to 2, 7, that's around there. So this is point Q. So this is the purple arrow is what the vector looks like at those starting and ending points. But remember, the only things that define a vector are the length, right? The magnitude and the direction. You can see both of these arrows have the same magnitude and direction. So oftentimes we just sort of shift the vector to the origin. But those are 2 valid ways of looking at this vector here. Now for the magnitude, right? You can either use the distance formula between these 2 points, right? All the way back from like the beginning of the school year, or you can just take the first component squared plus the second component squared and put it inside of a square root. So if you have that component form, right, then you can just go straight to using that formula there. And we get the square root of 26, which actually just go ahead and leave it like that if you get an answer like that. And the direction formula, that is the inverse tangent formula, right? It had inverse tangent of u2 over u1. And if you don't remember, right, the u2 and the u1 come from your component form, right? So there are whatever numbers are there and there. So in this case, we have 1 and 5, right? We would say that sort of 1 is this u1, 5 is this u2. So for this specific vector, we would calculate the inverse tangent of 5 over 1, which calculates out to, let's see, around 78.69 degrees. Make sure for this chapter that your calculator is in degree mode. Right? We don't really care about radian mode as much in this chapter. All right, let's look at this other one as well. Make sure we're doing this right. So the component form, we would do 1 minus negative 2, right? So we get 3 here. And then we would do negative 5 minus 6. So that would be negative 11. Right, so that would be your component form. Your magnitude would be 3 squared plus negative 11 squared. Right, so make sure that negative 11 is in parentheses so you don't get anything messed up in your calculator. That's 121 plus 9. That gives me 130 inside of the square root. So I'll leave that like that. And then inverse tangent of negative 11 over 3. Now, you might be wondering, do we need to do anything to this number? Right, so negative 11 over 3. When you put this into your calculator, you get negative 74.74 degrees. Now, the question is, you might remember there's a rule that we said you might have to add 180. Sometimes you don't, but sometimes you do. How do we know if we need to add 180 in this case? Really quick trick, right? Look at the x-coordinate. If the x-coordinate is positive, then do nothing. If the x-coordinate is negative, that's when you add 180. And so the way you can see that, right, if you want a more visual approach, if your vector is pointing to the right in any way, doesn't matter how steep it is, right, do nothing. If your vector is pointing to the left in any way, shape, or form, so all these green vectors, right, that's when you add 180 degrees. So in this case, because that 3 is positive, so let me get rid of those. Because this 3 is positive, we don't have to add 180 in that we can just leave this as our final answer. So those are the only two cases I want you guys to keep in your mind. You don't need to worry about adding 360 or anything like that. Just if it's pointing to the left, add 180. If it's pointing to the right, do nothing, right? Here we got a sort of rapid round of adding vectors, subtracting vectors, and scaling vectors. So we have some vectors defined above, so we just want to add them and subtract them. So like u plus v would be 2 plus 1, comma 9 plus negative 6, right? Well, that's going to be 3, comma 3. Nice. Let's do v plus w, right? V plus w, that's going to be 1 plus negative 11. And then negative 6 plus 3. So that's going to be negative 10, comma, negative 3. Awesome. Subtraction is pretty much the same thing, right? So for u minus v, we would do 2 minus 1, and then 9 minus negative 6. Right? Notice how it's pretty much the same as last time, except we got a minus symbol there. So now this is going to be comma 15. V minus w, 1 minus negative 11, negative 6 minus 3. Right? Feel free to pause the video and go back and make sure you understand how I'm doing some of these. I'm just going fast so that this video is not like an hour long or anything. Right? So 12, negative 9. We also have some scaling problems, right? So what I would recommend doing is rewrite the problem and then stick the vector in there. So the vector in place of that letter there, and then do your distribution. Don't try to do this in your head because you're going to make a mistake. I can almost guarantee you. Negative 3 times 2 is negative 6. Negative 3 times 9 is negative 27. Right? It's not that much extra work. Just make sure it's foolproof and that you don't miss some easy points there. Negative 2 times w. Right? So again, just sort of distribute it in. Right? So we get negative 2 times negative 11 is positive 22. Negative 2 times 3 is negative 6. Boom. And for these last ones, right, these are what we call linear combinations. Just remember, right, you do the scaling first, and then you do the addition, right? So it's just like how if you have multiplication and addition, do the multiplication first. Scaling is kind of like multiplication. So first things first, I would actually want to go ahead and replace these vectors with their component form. All right, so I'm just going to put that in for you, and then put 1 comma -6 in for v. All right, so distribute the 5, distribute the 3. That's our first step. So we get 10 comma 45 plus 3 times 1 is 3. 3 times -6 is -18. And then we add them together. So now we're going to get 10 plus 3 is 13. 45 minus 18 is 27. Boom. So just make sure you're doing that scaling first, because that's what you have to do first. Yeah, let's go ahead and just do this one as well, right? So 2 times this vector minus 3 times vector u. So again, distribute the 2. I'm going to go ahead and distribute the 3 and just leave the minus out in front there, right? So if you go back to the handout, I showed y'all 2 approaches to do scaling when your scalar has a negative there and you're combining a bunch of stuff. I would recommend just distribute the number in, leave the minus outside like this, so that we have 3 times 2, that's 6. 3 times 9 is 27. And then do the vector subtraction, right? I'd say that's the easiest way. -22 minus 6 is -28, comma, and then 6 minus 27 is -21. Boom. And then we have a nice little problem down here about unit vectors. So remember, a unit vector is just a vector that's being divided by its magnitude, right? So the unit vector for u would be the vector u divided by the magnitude of u. So if you can find the magnitude, you can find the unit vector. And I might just do maybe one example from here to save time, but you'll see the full solutions later. So this is the vector 2 comma 9 divided by, what is the magnitude? Well, we know that formula. That's going to be 2 squared plus 9 squared. In fact, it might be better to even rewrite it like this. 2 squared. That way we can see what the scalar is, right? The scalar is that big fraction in the front. And what is that? That's going to be 4 plus 81. That's 1 over the square root of 85 times this vector. And then, of course, we would want to distribute this in, right? So 2 times 1 over the square root of 85 is 2 over the square root of 85. 9 times that is 9 over the square root of 85. And I know your brains are probably saying, you know, this is not okay, but for the sake of vectors, we're going to leave these alone. It's actually better in a lot of cases to leave a vector like that. So go ahead and try out v and w yourself. It's pretty much following the exact same process. Just do it the same way and then check your solutions once I post the full solutions. But I want to make sure we have time for these because we didn't really get to go over problems like this as much. But this is honestly the most important part about vectors is the applications. So I'm going to give you guys really simple ones. The vector word problems can get very complicated, but because we didn't have as much class and time to go over these, I'm going to go over the really simple cases. So the first type of word problem you could have is you have some sort of velocity vector, and they give you the magnitude and the direction. Or they give you the direction in an implicit way, right? So Like here, for this airplane, the magnitude is 100 miles per hour, right? That is essentially how long this arrow is. That's the magnitude. The direction is given kind of by this reference angle here, right? We call this a reference angle. So we have an angle of depression of 30 degrees. And I'll give you guys the picture on the test of what the situation looks like. And the question is, what are the components of this vector? And actually, I would say doing this problem is actually not that tricky if you just remember some SOHCAHTOA, because remember, every vector creates a right triangle. Namely, in this case, we have, if you draw a line like that, we have a right triangle like this. And every single time you see a right triangle, you can always use SOHCAHTOA, right? So if that's my reference angle, the 30 degrees, then this is my opposite side. This is my adjacent. That's my hypotenuse, right? And so I can find the opposite and the adjacent, and guess what? Those are my components. That's how vectors work, right? So I want to find opposite and adjacent. Well, again, go back to SOHCAHTOA, right? It's probably the most important skill in all of pre-calculus is if you can use SOHCAHTOA. SOHCAHTOA, the SO part will give me the opposite side. Right? Tells me that sine of 30 degrees is equal to the opposite over 100 miles per hour. And I'll put another circle around this just so that's an O, not a 0, right? And then the CA part tells me that cosine of 30 degrees. Now you got to be careful here, right? Because sine of 30 degrees is going to be positive. But we know, because we're going down here, that the y-coordinate of our components should be negative, right? So we'll keep that in mind at the end. But essentially we can say cosine of 30 equals adjacent over 100. Right? So what do we get? If you solve for the opposite side, we get, well, 100 times sine of 30. Again, make sure you're in degree mode. It tells me 50 miles per hour. And that's not quite the answer. We'll correct that in a bit here. But the cosine one is going to be absolutely correct, right? So 100 times cosine of 30, if you solve for a there, you get about approximately 86.60 miles per hour. So that one's for sure correct. The only change we need to make to the opposite, because it's going down, that's the negative direction, is we just make it negative. And then that's our other component. So really, because they wanted the component form, let's go ahead and put these together, right? The component form is going to be 86.60, comma, negative 50. And then we put the units at the end like this, miles per hour. So there we go. That is the component form of this vector that we have in this diagram, this diagonal vector there. Right? So just using some basic SOHCAHTOA gets you the component form. The other really awesome application of vectors usually has to do with forces and in like a physics situation, especially net force. Net force is when all the forces acting on an object are just added together. And forces are usually viewed as two-dimensional or three-dimensional vectors. So for this question, it says find the net force as a vector. And it says, and I'm going to give you this hint on the test too, right? Net force is just the sum of those three force vectors, right? And we see them in the diagram. So we're just trying to add them all up, and whatever we get at the end, that's the net force. And here, notice what we've been given, right? We've been given magnitudes and maybe like a reference angle. Sometimes not, right? You can tell this has a magnitude, but they don't give us an angle. But we can definitely tell what the component form is pretty easily, right? Same thing with 75. We might have to do some work on this vector over here to figure out the component form. Because remember, you can't really add vectors and get the numerical answers without the component forms. So let's get the component forms here first, right? So f1 as a vector, what does the component form look like? Well, it's an arrow pointing to the right along the x-axis. That means, well, the component is just 50 comma 0, right? We're moving 50 units to the right and 0 units up or down. For this vector, f3, oh, that's f1, I should have wrote that. f3, the third force, the components, well, it's an arrow going down by 75. That's going to be 0 comma negative 75. Yeah. And remember, all these have units of newtons, so we could put those as well. Right? Because the downward direction on the y-axis is negative. I mean, it's just like with points. It's just like with points. And F2 is going to be a little bit trickier, right? So F2, we have to, again, use some SOHCAHTOA. Right? Now, one thing you could do is if you get the standard angle, there's a really nice little formula. So like we know this reference angle is 60, but if you don't want to have to think about what's positive, what's negative, here's a nice little trick. If you get the standard angle, which is the angle measured from the x-axis, right, which in this case is 120, all you have to do to get the components is take the magnitude, so 100, times, for the x coordinate, it's going to be cosine of the standard angle, so 120. For the y component, it will be 100 times sine of 120. So that's a nice little trick that's automatically going to make it positive or negative based on the situation. If you use 60 in your cosine and sine, just know that both those numbers are going to be positive from your calculator, but one of them should be negative, and we're going to see which one it is. All right, so let's actually calculate this. So I got 100 times cosine of 120. See, this is the component that should be negative, negative 50. And then 100 times sine of 120. We get about 86.60. Oh, we've seen these numbers before. Yes. But it's in a new context, right? So we should expect that vector to have a negative x component, right? Because it's going to the left. It's going to the left. And it should have a positive y component. It's going up, right? So if your signs don't match the picture that we see over here, you got a problem, right? You did something wrong. But now, right, if we want to find the net force, we might write it as F net. We would just add up all these vectors, right? So, let's just take these x components, not that one, this one, add all those up. So 50 plus 0 plus negative 50, that's an x component of 0. And then let's add up all the y components, right? So these numbers here. So 0 minus 75 plus 86.6. It's going to give me 11.6 newtons. And we would just leave the units out there like that. So this is something that physicists use all the time. They are always trying to figure out what is the net force on an object, especially when it comes to like space station stuff and anything having to do with space. They're going to be drawing little diagrams of forces and calculating net force. It's just a very, very, very helpful skill. And if you're taking AP Physics, you know exactly what I mean. You've probably been doing this the entire school year. So it's probably very easy for you if you've been taking physics. But super great application of vectors. Amazing stuff. Let me keep going here so I'm not running low on time. We also have the dot product, right? So the dot product of two vectors, remember we basically sort of multiply the components together and then we add those products. Yeah, so let's see what we get. We get 1 times 2, and then plus 5 times 3. So that gives us 2 plus 15, which is 17. Awesome. Let's just do the next one real quick, right? So we get 1 times negative 10 plus 5 times 2, right? I'm just using the components of these vectors. That's negative 10 plus 10. Hang on, that's 0, right? So there's something special about that. B dot C, that's going to be 2 times negative 10 plus 3 times 2. It's going to be negative 20 plus 6. It's negative 14. And the next question, which two vectors are orthogonal? There's a very easy way to tell which two are orthogonal. It's the one that gives you a dot product of 0, right? And that's only the middle option, right? So what we would say is A and C are orthogonal. And really, that's the only pair that are orthogonal to each other, because the other dot products, notice, did not give us 0. So those are not orthogonal. Remember, orthogonal is a very fancy word for perpendicular. Right? So it just means that they're at 90-degree angles. And if you draw vector A and C, you're going to see that. Let's find the angle between A and B. What was the formula? The formula was cosine of theta, the angle in between, is A dot B over the magnitude of A times the magnitude of B. So that's the angle between formula. Remember, this only gives you cosine of the angle, so you have to take the inverse cosine at the very end. But we know what A dot B is, right? We already got that answer. It was 17. Now we just need to calculate the magnitudes, right? So the magnitude of A is going to be 1 squared plus 5 squared. That's 26. So square root of 26. The magnitude of B is 2 squared plus 3 squared. Well, that's 4 plus 9. That's 13. Right. And so this gives us, let's get an approximate answer here. See what we get. We get about 0.925. If you ever get a number at the end here that's bigger than 1, you've done something wrong. You should always get a number in between -1 and +1. Right? Now, what do we do with that number? That's not the angle, right? The angle is the inverse cosine of that number, 0.925. So you do this at the very end. Inverse cosine of 0.925. So it gives you about 22.33 degrees. There you go. And make sure you're in degree mode, right? You want to be in degree mode. And just to save time, I'll let you guys do that other one with B and C. All right, 6.5. Calculate the following. So those are just some complex number addition and subtraction. Maybe I'll do the first one in the third one. So remember, just add the components. It's the same as vector addition, right? So you're going to get 3 plus 5 is 8. And then you'll have -2 plus 1, right? This has a coefficient of 1. So it's going to be -1i. Or, you don't have to write it like that. You could just say 8 minus I, right? Same thing. Multiplying, remember, you have to distribute it all out. There's no shortcut for this. So we'll have 2 times 3 is 6, minus 4i plus 3i, and then we'll get minus 2i squared, right? There are two i's there. So what is this going to turn into? It will turn into a positive 2, right? Because I squared is equal to negative 1. So we end up with 8 minus I. Oh, wow. Same answer as before. That was purely coincidence. That's really interesting. Calculate the absolute value. I'll do maybe two of these. I'll do maybe this first one, top left, and the bottom right. So what is the absolute value? It's the same thing as the magnitude formula. So you would take the components, the real component squared plus the imaginary component squared. We do not put the I here. We do not, don't put the I in the square root. That's not the component. The component is just the number in front. That's going to give us, looks like 64 plus 36. That's 100. And we're taking the square root of that. So it's going to be 10. So the absolute value was exactly 10. And you might notice it's kind of similar to a 3, 4, 5 triangle, except we have 6, 8, and 10. Right? So it's basically a 3, 4, 5 triangle scaled by 2. Let me do this bottom right one. So again, use the same formula. So this squared plus squared square root. Well, we get 3 over 4 plus 1 over 4. And that turns into 4 over 4 inside of a square root. Oh, hey, that's equal to 1. And that should make a lot of sense because this complex number is on your unit circle, right? So it's a distance of exactly 1 from the origin. So you should get 1. In fact, if you notice that at the beginning, you could skip all of this work and jump to the answer of 1 and just write a note. You could say like on the unit circle, right? It's a really nice intuitive shortcut to the answer. You don't have to calculate anything. But you can, if you wanted a foolproof mechanical way, just use the formula. You should get to the same answer. And let me do a couple from this page as well. So rectangular, I'll probably do maybe this one and this one here. So this complex number is written in polar form. It's actually easier to go from polar to rectangular. We also called it trig form, right? Trigonometric form. Because all you have to do is evaluate each of these things one by one, and then just distribute the 6 at the end. So first off, what is cosine of 60? Just use your unit circle. You won't have a unit circle on the test. You need to know this. But cosine of 60, I mean, I'm sure you know, is 1/2. And then sine of 60. What is sine of 60? That's radical 3 over 2. So I'll have plus I times radical 3 over 2. All right, so just evaluate those two functions. Now we distribute. Multiply by 6, and we get 3 plus I times 3 square root of 3. And that's our final answer here. The middle one, this is going from rectangular to polar. What you have to do is you have to somehow figure out how do I turn this into sort of a unit circle complex number. The first move you're going to have to do is you're going to have to pull something out of both terms. And you want to ask yourself, what does this look the most similar to as far as the coordinates on the unit circle? Well, if I think about it, it kind of reminds me of this coordinate on the unit circle. And that's sort of in the top left of the unit circle. And how do I get it to look like that? I basically just have to pull out a 2. Right, so I end up with this right here. And if you don't see kind of how I did that or why that's the case, just distribute the 2 back in, and you'll see that it's true, right? But now that I have a unit circle complex number, I can easily see what the angle is, right? Because trig form always needs some sort of angle inside of your sine and cosine. What angle creates this coordinate on the unit circle? That's going to be the angle 135. So my final answer is going to be 2 times cosine of 135 degrees plus I sine of 135 degrees. And that's my final answer. So going from rectangular to polar is a little trickier, but it can be done. You just need to sort of manipulate whatever you see there. You have to sort of think a little bit more creatively for that. So maybe try that third one on your own. And then I'll do one of these. So De Moivre's theorem, this is something I'll probably provide to you on the test. But essentially, right, this number, what this problem boils down to is you essentially take that number, you put it on as a power on this number, which that's your absolute value, by the way, right? That number in front, if your complex number is in polar form, that's your absolute value. You raise that number to the power 3, and then you're going to multiply these angles by that number 3. So we end up with 2 to the power 3 times cosine of, looks like 135 degrees, plus I sine of 135 degrees. And I don't want you to leave it like this, right? Make sure you actually calculate 2 to the power 3, which is 8. But you can actually leave it in polar form because really all I care about is whether or not you can use that theorem. And if you get this far, that's proof enough. Right. Okay, and again, just to save time, I'm going to go ahead and just do maybe 1, maybe 2 of these. Let's go ahead and maybe do 1. I'll do 1, and we'll do maybe 2, depending on how long this has gone. All right, so we're being asked to solve each triangle, all angles and all sides, right? How do we do this? Well, first off, notice what we have here, right? We have a side, an angle, and a side. If you ever have sort of a sandwich like that of your given values, you're going to use law of cosines first for sure. Notice how we have angle C. So we're going to have little c over here, little b over here, little a over there. Go ahead and label your triangle. And use the law of cosines, which is down here, right? Law of cosines. Yeah. Just go ahead and use it. So little c squared equals a squared, so 15 squared, plus b squared, 26 squared, minus 2 times a times b times cosine of c, right? Remember, that's equal to c squared, right? So what I'm going to do, I'm going to put the right side in my calculator and get the number there. 26 squared minus 2 times 15 times 26 times cosine of 35, and I get 262.06, right? And then at the end, right, take a square root. So we get that c is I should have put approximately. C is approximately 16.19. So that is side C. Now from there, right, so let me go ahead and label that 16.19. Notice what we have here now, right? We have an angle side pair, and let's say we're trying to find angle B. Well, we have a little b, right? So if we have two pairs and one thing is missing, we can use the law of sines now, right? So sine of capital B over 26 equals sine of 35 over 16.19. Right? So I'm going to go ahead and cross multiply here. We end up with, it looks like 16.19 times sine of b is equal to 26 times sine of 35. And we're trying to solve for b, right? So divide both sides by 16.19. Divide by 16.19. Those cancel. We have sine of capital B is equal to, let me calculate that whole right side there. 26 times sine of 35 divided by 16.19. That is about 0.9211. And to get B, I have to take the inverse sine of that number. Right, the inverse sine of that number, which it is giving me an answer of about 67.09 degrees. Right, so this kind of problem takes a good bit of work, right? It's not going to be easy. Oh, you know what? We're running into an issue here, though. Notice that's an obtuse angle. And we clearly have an acute angle. So what's the issue, right? The issue is that there are actually two values, two angles, where if you put them into the sine function, it spits out this number, right? So if you think about it, right, there are two angles that spit out that number. If I draw a little unit circle, where does sine equal 0.92? Well, that's going to be like really, really close here, right? It's either here. Well, actually, it's saying it's not that high, but maybe something like this, right? There's two places by symmetry. There's this angle and this angle. So this angle is what we got out of the calculator. Okay, so that, in one sense, that does make sense, but actually, we really want the other angle. Right? We want this one because that's the obtuse angle. That's the correct angle right here. So how do we find it? Well, let's think about the symmetry, right? If I can figure out the distance, the angular distance here, well, that's going to be the same as the angular distance here, and I could add that on to 67.09. So think about it, right? Just take a 90 minus 67.09. So one of those pink angles is 22.91. Let's double that. So two of those pink angles is 45.82. Let's add that to what our calculator gave us. So plus 45.82. And so we get a final answer of, and this should be a lot more reasonable, 112.91 degrees. And that is angle B. 112.91 degrees. That makes a lot more sense, right? Now, if you want to avoid all that nonsense, if you don't want to have to think about it as much, just do this, right? Use C and C, and then just use A and A, and you won't even have to worry about that, because look at angle A. It's an acute angle, so you're not going to run into that issue. You just won't. In fact, try doing the problem with angle A and angle C, and you should get what I got down here, right? So that's an easy way to check that works. And then lastly, to get angle A, well, let's just add them all up. They should add to 180, right? So 180 minus 35 minus the answer we just got. leaves me with angle A being 32.09. And so there's really only going to be one of these on the test. But if you can do any one of these, you'll be perfectly fine on it. Notice here, right, with number 4, I'm not going to do another one because I think this is like 45 minutes already. You'll see this full solution key later, but notice how this angle is really close to 90. So what you should expect for little c is that it should be very close to 20.2 squared plus 23.8 squared inside of a square root, right? The closer that angle is to 90 degrees, the more the law of cosines turns into, it essentially turns into the Pythagorean theorem, right? When theta is close to 90, when the angle is close to 90, basically that whole second term pretty much goes to 0, right? It almost affects almost nothing. So that would be really interesting. Maybe try for number 4. Maybe try to do it one way with the law of cosines. See what answer you get there, and then maybe try to use it using the Pythagorean theorem. And those answers, if you're doing everything right, should be very, very similar. It might even be hard to tell the difference. But anyway, I'm going to leave the rest to you guys. The only other thing I need to mention is, which unfortunately is not on the review, I think I'm going to go over it in class, but the visualization of vectors, right? So if I have a vector like this, and I give you another vector like this, if I don't give you any numbers, you should still be able to draw what the sum of those two vectors would look like. Right? So remember, all that is you take one of the vectors and you slide it up. You keep the same direction, but you start it at the head of the other vector. So something like this. Or you could do it with the blue. If you do it with the blue, you still end up at the same spot. So the place where that ends, right, whichever vector you chose to add, this black vector is the sum. So if we say that this is vector A, right, this is vector A, and that this is vector B, this is vector B, what we would say is that the black vector represents A plus B. And notice how I didn't need any numbers to do that, right? For subtraction, it's a little different, although it still follows the same idea. Let's say this is vector C, and we have vector, let's say this is vector D right here. The subtraction of these two, if you really think about it, let's say we're trying to find vector C minus D. What is that going to look like? It's going to look like this red vector. So this is the vector C minus D. And the reason for that is because if you add up this vector with this one, well, you have D plus C minus D. So the D and the minus D cancel, and you're left with C as the resulting answer. So it should make sense with the way vector sums work. And the only other thing too, right, would be scaling. So if I have a vector, let's call this vector F or something, right? If I scale this vector F by -2, the negative is going to flip it into the other direction, and the 2 is going to stretch it by a factor of 2. So I would basically have 2 lengths here, right? And I'd be pointing in the opposite direction. So this might be a nice little sketch of what the vector -2f looks like. Now, if I scaled by, let's say, positive let's say positive 3, right? I would basically be going the same direction. 1, 2, 3. I'd be pointing in the same direction. I've just been stretched out by 3. And of course, you can still do this with fractions too. If I wanted to do the vector 1/2 of f, that's going to be this little orange vector, right? That would be 1/2 of the vector f. It's half the length, the same direction. So just keep these things in mind, that you could also be expected to sort of draw out these scenarios. Like if I give you two vectors, that you can draw what the sum looks like, that you can draw what the subtraction looks like, or the scaling, right? So anyway, I'm going to go ahead and call it here. That was a lot of stuff. Good luck studying, guys. Let's try to finish strong here. We will have some interesting stuff after this test, don't worry. And then we'll just finish out the semester. So take care.